Thank you. So I'm going to give a brief update on what Copenhagen Atomics has been doing for the last year. But firstly, for you who might not remember, Copenhagen Atomics is a Danish molten salt reactor company developing 40-foot shipping container-sized reactor vessels with the goal of being able to scale to terawatt levels of energy. And we very much share the vision of Kirk. And we've chosen a route where the reactor is autonomously operated and completely sealed for 5 years at a time. And after 5 years, you throw away the reactor. And if it breaks before 5 years, you also throw away the reactor. So there's no possibility of maintenance or changing the software, anything. But we reuse the salt, and then we use heavy water as a moderator that doesn't degrade. So we can also reuse that after a 5-year time. And so a brief visualization of what that could look like. We're thinking of how to scale to terawatts. So we don't need like a bunch of small reactors placed in each municipality. We need to make big sites that can produce huge amounts of energy. And the Copenhagen Atomics business model is to build a reactor site that produces heat and sell the heat to the customer. So we will build, operate, own, and decommission the reactors. And in this visualization, it will be equivalent to 1 gigawatt electric if you coupled it to steam turbines. And each of these reactors are then shuffled every 5 years, and the vessels are stored by the back until decommissioning. So the primary waste we have here is fission products and activated steel. The potential of this is long-term for us to make breeder reactors. So unless you scale enrichment like 100-fold, you're not going to be able to reach global energy capacity with nuclear. So we have to have breeders to get there within decades. So this is what we're developing towards. Initially, we're starting with metal core construction, but we want to move to carbon-carbon composites. And with this, we can start on transuranics and transition to breeding within 3 to 5 years of operation, depending on the mixture. And that's because we have a very small fissile inventory, 200 kilos of transuranics, half a cubic meter of salt roughly, and then 3 cubic meters of blanket salt, and 3 cubic meters of heavy water. And something that was a surprise to us is that we can even start on 5% enriched uranium. And within the 5 years converts to a thorium cycle, but you still have the U-238 sort of poisoning your reactor breeding capabilities a little bit. So the way we're developing all this is that we're very focused on building. We're basically a team of tinkerers building all these machines, because before you can go build a commercial plant, you need to have something operating for a period in your labs. So when we started, we similar to many other people here in the room, found that it was hard to get pure salt, pumps, heat exchangers, all these components. So we decided to, all the stuff we couldn't find, to just make it ourselves. And through the past years, we've been very proficient at purifying the salt. So we started on small scale, 100-gram scale, and then moved up to like kilogram ingots. And we're at a point where we can consistently purify these to like 20 ppm of total impurities. And we've both done this for basic salts like fluoride, but also for our blanket salt, lithium fluoride, thorium tetrafluoride eutectic. And we've moved on to scaling up the production to be these 50-liter canisters. So still around 20 ppm of total impurities, but we need to scale this in order to build bigger loops that are going to turn into reactor prototypes. So we're actually scaling this an additional step to like a cubic meter sized vessel. And we're in the process of getting approval to handle 100 tons of thorium and 10 tons of uranium in Denmark. You need to start to get those sorts of volumes to start producing test reactors. So we've built these pumped loops that are sort of enclosed vessels that operate autonomously as well, where we've now built 15 of these, and we're constructing 10 more. And that's to sort of not just see that one works, but that they work in general. Once you start building more than one, you start finding new problems, and to get sort of reliability on a broad basis of loops. And they're then completely inerted and have a pump inside that is equivalent to like a 3 megawatt system, roughly. So all the components that we're testing is to prepare for a 1 megawatt test reactor, or we can sort of squeeze it into a smaller form factor. We also have 24 of these static salt test loops, and that's test corrosion and flanges, but mainly to just test systems again, test electronics reliability, And all of these are also working independently and uploading data. We do all the electronics in-house, and something that we're really proud of is that this year we started building these system with the consensus steering. So all those yellow units you see there have just an off-the-shelf Raspberry Pi inside of it. And they then all have to agree on the state of the reactor and what to do next. So if you had bit flops from radiation in one of them, it doesn't matter because the consensus has to agree on what to do next. So you can even have half of them die during a 5-year operation and it can still keep chugging. And they then communicate with embedded electronics that actuates valves and sensors, thermocouples, gathers all that data. Besides the electronics, then the workhorse of these systems are pumps. We heard a lot about pumps earlier. Copenhagen Atomics are making 2 types of pumps. The first one we made is a canned rotor pump. So the pump is connected to the motor and it's inside the furnace at 700 degrees and in a type of design that can tolerate radiations as well. So there it's then cooled by the salt and it uses a hydrodynamic bearing. So it's cooled and lubricated by the salt. And these pumps can generally function fairly well, but we don't see for long-term operation in a reactor where you have to have reliability of the components, not for safety, but for economic reason, that a hydrodynamic bearing is the most reliable thing. So we've developed a canned rotor electromagnetic actuated pump. This is the first prototype, but we're developing a couple more of them. Again, if you heard from the previous discussions, there's a motor that's actuating the rotor assembly through an electromagnetic field. And then you also have electromagnets levitating the whole rotor assembly so that it doesn't have any wearing surfaces, it's just free floating inside the salt. And this is something that industry has been making for a couple of decades, and they can in general reach tens of years of operation without maintenance. So we believe that this is something we can actually get to work for 5 years at a time inside of a sealed vessel without any maintenance at all. And this year we then produced our first non-fission prototype. So it's a 1-to-1 scale of a 1 megawatt reactor. So the commercial reactor is a 40-foot. This is a 1 megawatt, so it's a 20-foot container. The only difference between the two is the size of the pumps and heat exchangers. Everything else is sized for a 100 megawatt reactor. On the one side, you have all the electronics and heavy water. And on the right, you have a furnace with the salt circuits and the core. And so we don't have heat tracing on all the pipes. The whole right side for you is heated as a one furnace. And if the power drops, the pump stops and it drains back to the dump tanks. And for the salt, it would drain to the bottom and have passive decay removal through the bottom of the tank. So the way you shut down this reactor is not by having human operators, you just cut the power to it. That's the simplest way of shutting it down. So moving forward for us, we're building another non-fission prototype. The current one we're testing with water, we're building another one that will run with FLINAC, which is why we had to scale our salt production, because it needs 4 cubic meters of FLINAC inside of it at 20 ppm of total impurities. And as I mentioned, we've applied for a license to have large quantities of thorium uranium so that we can also produce the thorium salt that we've tested on small scale, but scale that up also to cubic meters of salt. And we hope to do that actually by the end of next year. And from there, we want potentially to build more of these systems and run those in parallels as well, similar to what we did with the loops. But our goal is to put fuel inside of one of these things and run it as a critical experiment for a few weeks by 2025. And at that point, we feel like we're ready to engage a licensing authority, because now we have all the experience that our equipment works. We've seen what would fail. We've iterated on the design to a point where we can get good advice on how to actually safely operate one of these. So lastly, I just want to briefly mention that we do a lot of open source development in software for modeling of molten salt reactors and neutronics. And it's all based on OpenMC. So if any of you are doing neutronics or modeling, please reach out or try and use some of our software. We try to make video tutorials on how to use it as well. So we made detailed CAD models of all the Oak Ridge reactors. One of them didn't have a name, so I called it ZPRE, Zero Power Reactor Experiment. And the one you see here is the that reactor test. So we've made detailed CAD models. You can download them, you can mesh them open source, and you can do neutronics on them. You can do continuous and batch-wise burn-up, and you can also do online geometry modifications to keep the criticality at 1 while you're doing burn-up. And we're working with ANL on implementing transient modeling to that also. And that's the idea, that we should have open source tools to work together as a community and sort of build on some common things and understandings. And I'll leave it at that.